Hi friends, in this video we will learn how to apply Big M method for a given LPP, for a given linear programming problem. What is the use of Big M method? Let us try to understand that first. In the previous video, we learned how to apply a simplex method in order to solve the given linear programming problem wherein the subject to constraint inequalities came up with more than two variables. And simplex method was a substitution for the graphical method. To overcome all the drawbacks by the graphical method, we made use of simplex method. Now this Big M method will help us to overcome some drawbacks that we also had in simplex method. In simplex method, we always noticed that we came across linear programming problem wherein the subject to constraint inequalities had only LHS which were lesser than equals to RHS. But we did not know how to solve if in a given LPP the subject to constraint has got LHS which is greater than equals to RHS and LHS which is equals to RHS. In such situation, we would be introducing surplus variables and artificial variables. Now let us learn what do you mean by surplus variables and artificial variables. In the previous video, we have understood the meaning of slack variables. Slack variables are nothing but a positive variable that is added to the LHS part of the subject to constraint inequalities in order to convert them into an equation. In a situation only wherein the subject to constraint has got LHS which is less than equals to RHS. Now, surplus variable is the same variable which is subtracted on the LHS part of the given subject to constraint wherein the LHS of the given subject to constraint is greater than equals to RHS, and along with the surplus variable for the same equation for the same subject to constraint inequalities we will also be adding an artificial variable. Surplus variable is nothing but a positive variable which is subtracted from the LHS part of the given subject to constraint inequalities, and also we will have an artificial variable added only in a case wherein the subject to constraint has got LHS which is greater than equals to RHS. And if in case we have the LHS which is equals to RHS, then we will only add the artificial variable. There we will not be in need of any slack or a surplus variable. Slack variables are used only when in subject to constraint the LHS are less than equals to RHS part, and surplus variable is used along with artificial variable only when the LHS part of the subject to constraint is greater than equals to the RHS part. So let us proceed with the solution. Since the given optimization function for a given LPP is a minimization function, we will first have to convert this into an maximization function. We have a simple formula for it. Minimum of z is equals to maximum of z complement. This is how we convert the minimization function z into a maximization function. Now with this, we will be also changing the signs of the RHS part of this function. So these will be minus 2x1 minus x2. So now let us start adding these surplus variables, slack variables and artificial variables for these subject to constraints respectively. The first equation has got the LHS part which is equals to RHS. With this, we understand that we only have to add the artificial variable for the first subject to constraint. That will be 3x1 plus x2 plus a1 is equals to 3. Now this second subject to constraint has got LHS which is greater than equals to RHS. With this we understand that we will have to subtract a surplus variable and add an artificial variable in order to convert these subject to constraint into an equation. That would be 4x1 plus 3x2 minus s1 plus a2 is equals to 6. With this, we have converted the second subject to constraint into an equation. Now, the third subject to constraints is a simpler one where we have the LHS part which is less than equals to RHS. So with this, we understand that we should only add the slack variables. The slack variable would be 2x2 plus s2 is equals to 4. Now we will have to bring all these artificial variables, surplus variables and slack variables back into the optimization function. Now first let me bring the first surplus variable. Although we have subtracted it here, we will be adding it here. It will be plus 0 s1 and the artificial variable will be having a negative sign here. It will be minus and we will prefix an variable m for a1. Similarly m for a2 and this will be plus s2. This is how we bring down all the values, all these artificial variables, slack variables and surplus variables into the z functions. Now we will have to bring all these values of the RHS part of this particular z function into the LHS. Now that would be z complement plus 2x1 plus x2 minus 0 s1 plus m of a1 plus m of a2 minus 0 s2. Now these are the values in your index row for the table. Now let us plot all these values into the table. This is the table. Let us plot all the values. The artificial variable a1 and a2 have a coefficient variable m, which is a huge value, and the value assigned for m is 100. And in the basic column we only consider the artificial variables and the slack variables along with the z function. We will not add any surplus variables into the basic variable column. We will only see that the z function, artificial variables and the slack variables are present here, and the values for a1 and a2 would be 100. Let us now start plotting the values. The values for the z row will be 2, 1, 0, 100, 100, 0 and a 0. Value for artificial variable row a1 would be 3, 1, 0, 1, 0, 0 and 3. Values for artificial variable a2 would be 4, 3, minus 1, 0, 1, 0, 6, and the values for s2 row would be 1, 2, 0, 0, 0, 1 and a 4. These are nothing but the values in the z function of equation what we had, and this is the value of the first subjective constraint. This is the value of the second subjective constraint, and these are the values from the third subjective constraint. Now with this we will have to start applying Gauss-Jordan method, but in the index row there are no negative values. So to avoid the confusions, we will again have to follow one simple formula. We will have to make use of this formula in order to find out the new values for the index row. New z row is equals to old z row minus 100 multiplied by a1 row plus 100 multiplied by a2 row. In simple, old z row will be subtracted by all these values which we get in this bracket. 100 multiplied by a1 row plus 100 multiplied by a2 row, and plus in case if I have a3 row plus 100 multiplied by a2 row. Now let us try to put all the values. Now these are the coefficients of the old z row minus 100 multiplied by all these values, all these coefficients in a1 row. 100 multiplied by 3 will be 300, 100 multiplied by 1 would be 100, 100 multiplied by 0 would be 0, 100 multiplied by 1 would be 100. Once again 100 multiplied by 0 is 0, 0, and 100 multiplied by 3 is 300. and let me put this in this bracket so that you people can understand the calculation easily. Plus 100 multiplied by all the coefficients in A2 row. 400, 300, okay, 300 minus 100, 0, 100, 0 and 600. Before we subtract these things directly, we'll just follow one simple method. We will just first try to add these values of the A1 row coefficients and A2 row coefficients which are multiplied by 100. With this, we come up with these values. This would be 900, 0, 0 plus 100 would be 100, 100 plus 0 would be 100, 0 plus of minus 100 would be minus 100, 100 plus 300 would give me 400, 400 plus 300 would give me 700. Now subtract all these by this. Let us bring down all these values here. 700, 400, minus 100, 100, 100, 0, 900. We will have to subtract them. 2 minus 700 would be minus 698. 1 minus 400 would be minus 399. 0 minus of minus 100 would be 100. 100 minus 100, 0. 100 minus 100 would be 0. 0 minus 0 is 0. 0 minus 900 would be minus 900. So now this is the new value for a Z row. Let us try to plot a new table along with these new values for the new Z row. Now let us plot all these values of the new Z row here. Minus 698, minus 399, 100, 0, 0, 0, and this would be minus 900. Apart from the new values for the Z row, the values for all the other 3 rows would remain the same. Let us bring down the same values. We brought down all the values of the other remaining 3 rows to the new table here as they are. Now with this, we are now about to proceed with the Gauss-Jordan method. According to Gauss-Jordan method, consider the index row, and amongst the index row, except the solution part, amongst the basic and non-basic variables, consider the least negative value. The least negative value here would be x1. The value for the column x1 this column would make up to be the pivot column. Now we will divide all these values in the solution except for the index row. We will consider all the other 3 rows and divide the values of pivot column values for these and find out the minimum ratio. 3 divided by 3 would be equals to 1. 6 divided by 4 will give me something 1.5, and 4 divided by 2 would give me 4 divided by 1 would give me 4. So with this, identify the minimum value. The minimum value here is 1. So this row would consider to be the pivot row or the leaving row. Now this is the pivot column, and this is the pivot row. Now follow the same Gauss-Jordan method steps. Find out the A1 will be replaced by x1. Replacing A1 by x1. Now that means A1 will be replaced by x1. And how do we find out the values of x1 row, new x1 row? We have a simple formula. New x1 row is equals to old A1 row whole divided by the pivot column value for that particular row. The pivot column value for this particular row. Now bring down all the values of the A1 row. Now, this is the formula to find out the new Z row. New Z row is equals to old Z row minus of the pivot column value for that particular row, which is minus 698, multiplied by new X1 row. Let us try to find out the values for the new Z row. These are the values of the new Z row. First, I brought on all the values of the old Z row minus, I multiplied minus 699 with all the values of the new X1 row. I just got them as minus 698, minus 698 divided by 3, 0, minus 698 divided by 3, 0, 0 and minus 698. After subtracting all these coefficients of new X1 row multiplied by minus 698 and along with these old values of the old Z row, we come up with the new values for the new Z row. Similarly, find out the values for new A2 row. A1 row will not be finding. Why? Because A1 row is already been replaced by X1 and for that we found a new X1 row. So now we will have to find out the values for new A2 row and S2 row. This is the formula we will have to follow in order to find out the values for the new A2 row. New A2 row is equals to old A2 row, means the current values of the A2 row multiply minus the pivot column value for that particular row, which is nothing but 4, multiplied by new X1 row coefficients. Those are nothing but these. So let us bring down the values of the old A2 row and new X1 row multiplied by 4. I have brought on the values of the old A2 row, which are nothing but 4, 3, minus 1, 0, 1, 0 and 6, and minus 4 multiplied by new X1 row. 4 multiplied by all the coefficients of new X1 row. This would be 4, 4 divided by 3, 0, 4 divided by 3, 0, 0 and 4. After subtracting the coefficients from both of these rows, I will come up with these values. So these are the new values for the new A2 row. Similarly, let us find out the values for the new S2 row. And the formula to find out the values of new S2 row is new S2 row is equals to old S2 row minus the pivot column value for that particular row. The pivot column value for this particular row is 1 multiplied by new X1 row. After applying the equations, the value of new S2 row are 0, 5 divided by 3, 0, minus 1 divided by 3, 0, 1, 3, which makes up the new value for the new S2 row. Now let us plot all these new values into a table. New Z row value, new X1 row value, new A2 row value and new S2 row values. Now I have plotted the new values of all the rows in the new table. We will still have to go for the next iteration. How do we conclude that we have one more iteration to go with? Why? Because in the index row, I still find a negative coefficient. There is one variable that is holding a negative value. So this indicates that I will have to go for the second iteration and follow the same Gauss-Jordan method. Now first identify the pivot column. Consider the index row and except the solution part only amongst these basic and non-basic variables. Identify the least negative value. The least negative value here would be minus 166.3. So this will be the pivot column. Now try to divide all these values by the solution and find out the minimum ratio. Except for the index row. The minimum ratio for the for new X1 row would be 1 multiplied by 1 divided by 3 would be equals to 3. And for this new A2 row, it would be 2 divided by 5 divided by 3. Sorry, 1 divided by 3 is equals to 3 and 2 divided by 5 divided by 3 is equals to 1.2 and 3 divided by 5 divided by 3 would be equals to 1.8. Now find out the minimum value amongst these column. The minimum value amongst this whole column is 1.2. So with this we conclude that row number A2 row or row number 3 would be the leaving row. So this is called as the pivot row. In the first iteration, A1 was replaced by X1 and in the second iteration, A2 will be replaced by X2. The same way how we followed in the first iteration. Replacing a2 by x2, we will come up with a new x2 row. And how to find out the values for new x2 row? New x2 row is equals to current x2 row whole divided by 5 divided by 3. Now let us try to find out the values for new x2 row. I have brought down the old values of the A2 rows, and since it was a division part where it was 5 divided by 3, when I bring down to the multiplication step, it would be reverse. It would be 3 divided by 5. So 3 divided by 5 multiplied by 0 would be 0. 3 divided by 5 multiplied by 5 divided by 3 would give me 1. 3 divided by 5 multiplied by minus 1 would be minus 3 divided by 5. 3 divided by 5 multiplied by minus 4 divided by 3 would give me 4 divided by 5. 3 divided by 5 multiplied by 1 would give me 3 divided by 5. 3 divided by 5 multiplied by 0 would give me 0. 3 divided by 5 multiplied by 2 would give me 6 divided by 5. So this makes up the new value for the new x2 row. Now with help of this new x2 row, we will have to find out the new values for all the other existing row. For the row z, for row x1 and for row s2. Let us try finding the new value for the new z rows first. I have brought on the values of all old z rows, and I have multiplied the pivot column value for that row, which is minus 166.3, with all the values of the new x2 row, and I have plotted them here. After subtracting these both, we come up with new values for the new z row, which is 0, 0, 0.2, 99.6, 99.8, 0, minus 2.4. Similarly, let us try to find out the value for new x1 row. These are the values of the old x1 row, and 1 by 3 multiplied by all the values of new x2 row, and after subtraction we come up with this value for new x1 row. Similarly, we have also found the values for s2 row. The equation would be old s2 row minus pivot column value for that row. Pivot column value for this row is 5 divided by 3. 5 divided by 3 multiplied by new x2 row. We come up with this values. So in the second iteration, now we have found the new x2 row, new z row values, new x1 row values, and new s2 row values. Now let us try to plot all these values into the table again. We have now plotted all the new values that we found in the second iteration for each row in the table. Now try to check the index row values. We have to see that there are no negative values in the index row for all the basic and non-basic variables. We find that all the basic and non-basic variables have got all positive values. All the values which are 0, either 0 or greater than 0. So with this, we conclude the problem has reached the initial basic feasible solution. The reason why we introduce artificial variables with a huge value m is to find out the initial basic feasible solution. So with this, we conclude that the problem has reached its initial basic feasible solution, and the value of x1 is 0.6, value of x2 is 1.2. Let us try to substitute all these values into the objective function and find out the value for z. After substituting these values of x1 and x2 into the z function, we come up with 2 multiplied by 0.6 plus 1 multiplied by 2, which is equals to 2.4. With this, we conclude the value of x1 to be 0.6, value of x2 to be 1.2, and value of z to be 2.4. This is how we apply Big M method or chance penalty method in order to find initial basic solution for a given linear programming problem. Thank you.